Okay, girls, so I've been asked to just go through the graphs with you. So I'm going to go through the normal reaction rate graphs as well as the Maxwell-Boltzmann graph. Okay, so this is just a bit of revision. So I want to make it clear that you need to have a look what's on your y-axis. Now, the thing about the y-axis is that it can be looking at products or reactants. Okay, and it could be looking at their moles, their change of moles over time, their change of concentration over time, their number of particles over time, and their change of mass over time. And so this graph is going to show a change of these over time. Now, if you're working with, and I'm going to use highlighters, please, you never use a highlighter to draw a graph, okay? But I'm going to show you here so that you can see the different colors. So if we are looking at products, okay, so I'm going to highlight products. So that would be pink. Now, if you think of, we're going to look at the change of products over time. That means we're going to start with nothing. So we're going to start at 0, okay? So, and the slope can be quite steep at this stage because in the very beginning is the highest, sorry, I see this thing's losing focus all the time. At the very beginning, this is the highest rate that you're going to get because you have a high concentration of reactants, and so your reaction rate is quite high in producing lots of products. Okay, so you'll see here as you go, it starts to decrease. Can you see the gradient slowly decreasing? And it can decrease, 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 decrease until it reaches a horizontal line. Okay, so what that horizontal line means is that if you look back here at what the reading is of that horizontal line, so let's extrapolate that backwards. So I'm going to just do a dotted line going back. So what that means is number of moles or concentration or number of particles or mass. This is going to be the maximum amount of any of those that we're going to produce. And so you don't have any more reaction happening. And so that's why the gradient goes to 0 over here, because there is no more reaction. You've used up all your reactants and you've made the maximum amount of product that you can possibly make. And so over here we have a 0 reaction rate because it has stopped. And you can now see that this is quite a high gradient compared to over here. If I were to have a look, a straight line like that, and look at the gradient at this point of the graph, you can see, look at that gradient slope compared to that gradient. It's a lot less steep. So remember I said to you, you can always go with a ruler and you go there on the gradient and you pick a point. So if you can even do this with a piece of paper, and we're going to pick one point on your ruler, okay, and we're going to make sure that that point is touching the graph at all stages. So as you move, can you see how my gradient's changing? I'm just keeping that point fixed on the graph, and I'm moving that point, and you can see how my gradient's changing and changing and changing. Look how it's flattening out. Okay, compared to here where it is quite steep, and then over here where I'm touching that. Remember I said to you, you can use like a 5 on your ruler to do this, and just keep the 5 touching the graph, and you can see how it's approaching 0 all the time, a 0 gradient, until it really does reach a 0 gradient. Okay, so that means that the reaction rate excuse me, over time decreases, and that is because we are running out of reactants, and so the concentration of reactants is decreasing, and so the concentration of the reactants is decreasing, and so the reaction rate is decreasing. Remember, the products are just being produced based on the reaction rate of the reactants. Okay, so if the reaction rate is decreasing, then you can see it over there. So this is the amount of products produced over time, and you're going to go up like that. Okay, so now let's take a look at what happens when we're looking at reactants. Okay, so remember, you can look at reactants: change of moles, change of concentration, number of particles, and mass. So what we're doing here is we're doing the same thing. We are looking at the reactants being used up. So we're going to start at a higher point. So let me make it a bit there. And we're going to see that we're going to have quite a sharp or a high gradient to begin with, because our concentration of reactants is quite high in the beginning of a reaction. And as we go, we can see my gradient dropping. Now again, remember, you can take your ruler and you can follow, and you can literally see the gradient of my ruler changing as you are touching with that one point. Okay, now with reactants though, they are going to reach 0. Okay, so they're going to reach 0 line, and don't be scared to draw on your x-axis. Okay, now why would they reach 0? Because you are using up all your reactants. Okay, next year I'm going to teach you about reversible reactions, and then they might not go to 0, but for now they can go to 0. Okay, if they don't go to 0, that means some of the products are making reactants again. Okay, but don't worry about that. And now you can see how the gradient goes from quite steep, so high reaction rate, and it's losing gradient. The gradient's decreasing, and so the reaction rate is slowing down. Why? Because the concentration of the reactants is decreasing. Okay, and according to the collision theory, there'll be less particles per unit volume to collide, which means there will be less particles for effective collisions per unit time, and therefore the reaction rate is low. And then when it reaches 0, again, we zero off. That means we've got no more reactants left, and the reaction is done. And so the reaction rate is 0. All right, I hope this helps. Let me just do one last thing. So remember, I said to you, if they give you, if they say, okay, well, this reactant has a higher volume, so let's go an increased volume, okay, or we have an increased mass, okay. Now the only thing that affects the reaction rate is concentration. Now I want you to think. I know you're going to say something like, but surely if you've got a higher concentration, you've got more particles, therefore it must be you must be making more product. Be careful about that, because we are meaning that if you change your concentration, we are not changing the number of moles, we are changing the volume. So if you're going to increase the concentration, we keep the moles the same, but the volume decreases. Okay, because that means that you've got more particles per unit volume. That's why it's important for you to say per unit volume, because we've just decreased the space that they're in. Okay, and if you decrease the concentration, you keep your moles the same, but the volume has increased. So they've got more space. Remember this whole thing about the little kids, the grade 1s in my class. So we're keeping the number of kids the same, but what we are doing is we're changing the volume of the room. So imagine having the same number of kids, and let's say we put them on Grace Trinity's small field, okay, and we tell them to run, okay, and they will knock into each other, but not, and quite effective, quite a lot. But then we tell them go up to in front of St. Dex and go run on that field, that whole massive field. So we are decreasing the space that they can run in. Remember, volume is 3-dimensional for liquids. So whereas we can only really use, the kids can't fly, so we can't use a 3D model for that. But that's what I want you to get, is that we are not changing the number of moles when we are increasing or decreasing concentration. We are just changing the volume that they're in. So if they're in a small volume, there's going to be a lot of collisions. If they're in a big volume, there's not going to be that many collisions per unit time. Okay, so that's why concentration changes the reaction rate without changing the yield. Okay, so if we increase a volume of a reactant or a mass of a reactant, Okay, that means we are actually adding more particles to the solution. Here we're not adding more particles, we are just changing the volumes. We're adding lots of water. If you're decreasing the concentration, it's going to be more dilute, so you're adding lots of water. If you're increasing the concentration, you're not adding that much water. Think about how you all make Milo. You use like 5 or 6 teaspoons of Milo, I'm sure, and then you put like a drop of milk in it. I know you guys. And then when your parents make Milo, they put 3 spoons in, not even as much as they say on the tin, and then they fill it with water and maybe some, if you're lucky, some milk. Okay, so the concentration is quite low there, and that's not nice. Okay, so here you have high volume, high mass. That means you're adding more of the particles. Okay, without changing the concentration, you're just adding more. So if there's an increase in volume or increase in mass, remember you can also have a decrease. So if you're increasing, that means that you are going to have more reactant being made, product being made. Okay, so this is with an increased volume or an increased mass. Okay, let me just put mass there so you don't get confused. Not concentration. If you are only increasing the concentration, you're going to land up on the same spot here, but you're going to have a steeper curve and you're going to reach the flat line sooner. Okay, so if you're going to then decrease the volume or the mass, you're going to land up over here and you're going to make less. So this is a decrease in volume or a decrease in mass. So you haven't done anything to the concentration, but these don't affect. Remember, the collision theory says only concentration, pressure in gases, and temperature, catalyst, and surface area affects the concentration. The reaction rate. Let me show you now. So if you increase the concentration of, that's all you do. You increase concentration. So that means you get. So over here we know. Here is where, let me do this in pink, sorry. Here is where, don't you love my pens? You know, you got this for me, Mr. Enslin, S. Enslin, because he knows I love these pens that do all this. So this is the time that it took to get to 0 gradient. Now, if you increase a reaction rate by increasing the concentration, sorry, that wasn't really a nice curve there, but anyway, can you see here? Don't you hate yellow highlighters? They always pick up the other colors. Have a look here. This is the time where the yellow got to its maximum product, and it got to the same maximum product. So the yellow is an increase of concentration. Okay, and obviously if you had a decrease in concentration, you would have a curve like that, but it would still reach the same level, the same amount of products being made. Okay, the same thing here. If you increase your concentration, it would be below, because remember you got a steeper curve and it would really reach the horizontal line, sorry. So you got a steeper curve and it would reach the horizontal 0 here line earlier than the green. Okay, I hope this helps. Please let me know if I've just confused the hell out of you. Okay, let's take a look at this. Now, I know a lot of you are going, but how can we only look at the area underneath? What they do with the Maxwell-Boltzmann is that, yes, we do plot a line. Okay, we plot a line and we say, okay, so the line is number of particles. So here we have high number of particles. Here we've got a lower number of particles. And here we have energy. So we have, and you're starting at 0 here and you're building your way up to high energy. So here we've got low energy and so on. But if we times these two together, like we did in motion graphs, if we times them together, we get the area. And we are looking at the particles with energy. Okay, so, and you can even see here we have a lot of particles with this amount of energy. Here we have a little bit of particles with that amount of energy. But what we're going to do is we're going to look at the area underneath. So an important thing here is to look at the activation energy. So at some stage there will be the activation energy. Okay, so if you look here, that's the energy here, and it's the minimum amount of energy for particles to react. So that means anything above that energy is energy more than what is required. And so if we had to draw our area, we're looking at particles and energy together. We say, okay, then that under there is the area, the number of particles that have enough energy or sufficient energy to react. Okay, that means all of those don't have enough energy to react. So we need to do something to get them to a bigger area. So what can we do? If you add a catalyst, according to the definition, the catalyst decreases the activation energy. So remember, we have, this is like the entry level over here. The activation energy is the minimum requirement. All of these particles after that have enough energy. Okay. Now, what if I lowered the entrance level? Imagine this is like a entry level to university. I'm now lowering. Can you see that if I lower, I have that energy and all of that energy now that they can have in order to have enough sufficient amount of energy. So if I were to look at that concentration now, that means that all of these, now I don't want you to get confused. That means that that orange is no longer, oh, sorry, you can't even see anything. That means that that energy is no longer there. The orange energy has disappeared because we've added a catalyst and now there's a new energy, activation energy. Okay, so don't worry that I'm showing you two here. The blue activation energy is now new because we've added a catalyst. Okay, so we've lowered the entry level for bonding. Okay, our new minimum energy is further down the line. It is at a lower energy level, and so more particles will have sufficient amount of energy per unit time. Now, while I'm on this, girls, I want you to realize that when you are dealing with the collision theory and you're explaining something, if something has something to do with the energy, you talk about the energy. If something has something to do with the concentration, you talk about the number of particles per unit volume, okay? You can't say, oh, the temperature has increased, therefore the number of particles per unit time has increased. That doesn't relate. Okay, anyway, so now you can see the green area has increased the number of particles. So the green area, that means there's more particles with sufficient amount of energy, and so the reaction rate will be faster. Notice that I didn't change the line here in any way. Okay, so let me take a look at the others now. Sorry, I forgot to draw a graph here. So I'm going to just draw one like that quickly and one like that. Okay, so remember we have energy, okay, number of particles, energy. Okay, so now what can change? Now we change the temperature. We increase the temperature. I'm going to show you an increase and decrease. Okay, so we increase the temperature. So remember we said that if you watch that other video with, was it Tyler? I can't remember. This area doesn't change. The area can't change. Why is that? Because the number of particles can't just magically change if you increase the temperature. Okay, so you've got to keep the area the same. However, the number of particles, the highest number of particles, all the particles will land up having more energy. And so there's a shift. There's a shift in that. Now, it doesn't mean it has to be higher, but what could happen is that could happen. Notice how the peak moves in that direction, and we land up with going from there to there. Our peak where our maximum amount, sorry, it's a little bit over, where our maximum amount of particles is, they have increased in energy, because energy is temperature. If you increase the temperature, you increase the energy. Okay, so we've not decreased the, or we shouldn't have decreased the area. So actually I could have made it more like that, because this area here that I've now added to the graph should equal to that area there that we've lost from the graph. Okay, so this is now the area under the graph. So can you see it's so much bigger than this underneath compared to that? So that means that we have now got more particles with a sufficient amount of energy. If we consider this as the activation energy over here, of course. Okay, so let me just put it here so that this makes more sense. So I'm going to just say this is my activation energy over there. Okay, now obviously if you decrease the temperature, now it's going to move in that direction. Okay, but now remember, you've got to keep your area. So what happens is that your peak gets a bit higher over here, and you land up with lower amounts. And so you can see here how by activation energy here, we've got less particles with sufficient amount of energy because we've decreased the temperature. Okay, so this is a temp decrease, and this is a temp increase. Okay, and so you can see, look at the area of pink compared to the area of purple. So more particles per unit volume have sufficient amount of energy to collide. Okay, therefore increasing the number of collisions because they're going to be moving a lot faster, and so on. Now, another thing you can do is you can, what can you do? I can't remember now. You can increase the concentration, okay? But all the concentration does, because it doesn't change the amount of energy you've got. So all the increase of concentration does is it increases your whole graph like that. So it increases the surface area, but can you see that the gradient, the graph is pretty much the same? The peak is in the same position. That's because we're not changing any of the energy, we're just adding more particles. So it's only going to go up or down here. Okay, so it's going to go up if you've got a higher concentration, high conc, okay, or it will go, what color haven't I used? Blue. Or it will go like this. I just want to make sure I do this properly. And this is going down because we're going to decrease the conc. Okay, and then you can see how that energy under that line is going to be quite small compared to the area of that black line compared to the area of the orange line. Okay, so that's what makes it increase the reaction rate. I think that's it, because you can only really change your activation energy and your temperature if you're going to do this. If you do the pressure, it's going to do the same thing as this. Okay, the pressure and concentration will do the same thing if you've got gases. So girls, I hope you understand now. I hope this has made it a bit clearer. Please ask me questions if you are still not sure. I will teach this to you until I die to make sure you get this. These are very important graphs. Okay, all right girls, have a successful study time.